Question 1. What is data drift in the context of ML ops? Option A. A sudden, catastrophic failure of a deployed machine learning model. Option B. Changes in the statistical properties of input data, or the target variable over time, affecting model performance. Option C. The process of moving data between different storage systems in an ML pipeline. Option D. A technique for improving model accuracy by adding more diverse training data. The correct answer is, quote, changes in the statistical properties of input data, or the target variable over time, affecting model performance. Here's the explanation. Data drift refers to the shift in data distributions between the data a model was trained on and the data it encounters in production. This shift can significantly degrade a model's performance and is a critical concern in MLOps. Question 2. A fraud detection model was trained to identify specific patterns in transaction amounts and locations. Over time, fraudsters begin using entirely new methods, causing the asterisk relationship between input features, transaction details, and the target variable, fraudulence legitimate, to change. Which type of data drift does this scenario primarily represent? Option A. Covariate drift. Option B. Label drift. Option C. Concept drift. Option D. Feature engineering drift. The correct answer is concept drift. Here's the explanation. Concept drift occurs when the underlying relationship between the input features, X, and the target variable, Y, changes, meaning the concept the model is trying to learn has evolved. New fraud schemes changing the input-output relationship is a classic example of concept drift, as the meaning of fraud has shifted. Question 3. An ML ops team wants to proactively detect data drift in a production model. Which of the following is a common statistical method used to quantify the difference between current production data distributions and a baseline? Option A. Principal component analysis, PCA. Option B. Kullback-Leibler, KL. Divergence. Option C. Support vector machines, SVM. Option D. Gradient boosting. The correct answer is Kullback-Leibler, KL. Divergence. Here's the explanation. Kullback-Leibler, KL. Divergence. Jensen-Shannon, JS. Divergence, Wasserstein distance, and population stability index, PSI, are common statistical measures used to quantify the difference between data distributions for drift detection. PCA, SVM, and gradient boosting are machine learning algorithms, not statistical drift detection metrics. Question 4. A critical ML pipeline for financial fraud detection suddenly starts producing an unusually high number of false positives, and logs show errors related to unexpected data types. Investigation reveals that an upstream system recently changed the Schema transaction_amount field from a numerical type to a string and renamed customer_ID to account_holder_ID. This scenario is a clear example of what ML ops challenge. Option A. Concept drift. Option B. Data drift. Option C. Model decay. Option D. Schema drift. The correct answer is schema drift. Here's the explanation. Schema drift refers to unexpected changes in the structure or format of data, such as column renames, data type alterations, or additions/removals of columns. These changes directly impact data quality and pipeline stability. Question 5. Which of the following is a primary detection mechanism and a key mitigation strategy for preventing schema drift from breaking ML pipelines? Option A. Detection, A/B testing. Mitigation, regular model retraining. Option B. Detection, schema validation against an expected baseline. Mitigation, implementing data contracts. Option C. Detection, monitoring model accuracy in production. Mitigation, using larger compute instances. Option D. Detection, analyzing feature importance. Mitigation, manual data cleaning after every ingestion. The correct answer is detection, schema validation against an expected baseline. Mitigation, implementing data contracts. Here's the explanation. Schema validation, comparing the current schema to an expected schema, is a key detection mechanism. Implementing data contracts, formal agreements on data schemas, is a primary preventative mitigation strategy to avoid unexpected changes. Question 6. A data scientist notices that the average income of customers in their training data has gradually increased over the past 6 months, even though the column name and data type for income remain unchanged. At the same time, the relationship between income and the target variable, purchase_likelihood, has also weakened. Which two distinct MLOps challenges are being observed in this scenario? Option A. Schema drift and model decay. Option B. Data drift and concept drift. Option C. Schema drift and data quality issues. Option D. data quality issues and model decay. The correct answer is data drift and concept drift. Here's the explanation. A change in the statistical properties or distribution of feature values, like average income increasing, is data drift. A change in the relationship between input features and the target variable, like correlation weakening, is concept drift. Schema drift refers to structural changes, which are not present here. Question 7. What is the primary problem that a feature store aims to solve in the MLOps lifecycle? Option A. Automating model retraining and deployment. Option B. Ensuring consistent feature definitions and values between model training and real-time inference, training serving skew. Option C. Providing a centralized platform for model versioning and artifact management. Option D. Reducing the complexity of hyperparameter tuning for machine learning models. The correct answer is ensuring consistent feature definitions and values between model training and real-time inference, training serving skew. Here's the explanation. The overview explicitly states that the primary goal of a feature store is to address challenges like feature reusability, consistency, freshness, and low latency serving, with a key focus on mitigating training serving skew. Question 8. Within a feature store architecture, what is the main functional difference between the offline store and the online store? Option A. The offline store is for raw, untransformed data, while the online store is for processed, engineered features. Option B. The offline store is optimized for batch access and historical feature values for model training, while the online store is optimized for low latency, real-time lookups for inference. Option C. The offline store holds features for categorical variables, while the online store holds features for numerical variables. Option D. The offline store stores deprecated features, while the online store stores only active and current features. The correct answer is the offline store is optimized for batch access and historical feature values for model training, while the online store is optimized for low latency, real-time lookups for inference. Here's the explanation. The text clearly differentiates their purposes. Offline store, a durable, scalable storage layer optimized for batch access, used primarily for generating training datasets, and online store, a low latency, high throughput storage layer optimized for real-time point lookups, for online model inference. Question 9. A feature store is best described as a specialized layer that is typically built on top of, or integrates with, which existing data infrastructure components to perform its functions. Option A. Version control systems like Git and CI/CD pipelines. Option B. Model registries and experiment tracking systems. Option C. Data lakes or data warehouses. Option D. Application monitoring dashboards and alerting systems. The correct answer is data lakes or data warehouses. Here's the explanation. The comparison section clarifies. A feature store is often built on top of or integrates with a data lake or data warehouse. It leverages these for its underlying offline storage, but adds ML-specific capabilities. Question 10. What is the defining characteristic of a data lake's approach to data storage, especially when compared to a traditional data warehouse? Option A. It enforces a strict schema on data before storage, schema on write. Option B. It primarily stores highly structured and clean data for predefined reports. Option C. It stores vast amounts of raw data in its native format, applying schema only when data is read, schema on read. Option D. It is optimized for high-performance analytical queries on transformed data. The correct answer is it stores vast amounts of raw data in its native format, applying schema only when data is read, schema on read. Here's the explanation. The schema on read approach, allowing raw and diverse data storage without prior transformation or a predefined schema, is a fundamental differentiator of data lakes compared to data warehouses, which typically enforce schema on write. Question 11. Which of the following is not typically considered a core feature or component of a data lake architecture? Option A. Support for diverse data types, structured, semi-structured, unstructured. Option B. Cost-effective storage leveraging object storage services. Option C. Decoupled storage and compute layers. Option D. Exclusive reliance on SQL-based processing engines for all data access. The correct answer is exclusive reliance on SQL-based processing engines for all data access. Here's the explanation. Data lakes are designed for flexibility and can be accessed by various processing engines, including distributed processing frameworks like Apache Spark, serverless query engines like AWS Athena, and machine learning platforms, not exclusively SQL-based engines. Question 12. In an MLOps context, Which concept describes the evolution of data lakes by adding data warehouse capabilities like ACID transactions, schema enforcement, and time travel directly on top of object storage? Option A, data mart. Option B, feature store. Option C, data mesh. Option D, Lakehouse architecture. The correct answer is Lakehouse architecture. Here's the explanation. The Lakehouse architecture combines the flexibility, scalability, and cost-effectiveness of data lakes with the reliability, transactional capabilities, ACID, and schema enforcement typically found in data warehouses. Technologies like Delta Lake, Apache Iceberg, or Apache Hudi enable this. Question 13. Which of the following is not one of the 4 key characteristics typically associated with a data warehouse? Option A, subject-oriented. Option B, time-variant. Option C, non-volatile. Option D, transactional-oriented. The correct answer is transactional-oriented. Here's the explanation. Data warehouses are designed for analytical processing, OLAP, not real-time transactional operations, OLTP. Their 4 key characteristics are subject-oriented, integrated, time-variant, and non-volatile. Question 14. In the context of ML ops, what is the most critical role of the transformation BT phase in a data warehouse's ETL/ELT process? Option A, to simply load raw data directly from source systems into the warehouse. Option B, to primarily reduce the overall storage footprint of the data. Option C, to clean, standardize, aggregate, and integrate data into high-quality, ML-ready features. Option D, to provide real-time transactional updates to the data. The correct answer is, quote, to clean, standardize, aggregate, and integrate data into high-quality, ML-ready features. Here's the explanation. The transformation phase is crucial for ML ops because it prepares raw data by cleaning, standardizing, aggregating, and integrating it, making it suitable for feature engineering and robust model training. Question 15. How does a data warehouse typically complement a data lake in an ML ops ecosystem, particularly concerning feature engineering for model training? Option A, a data warehouse is used to store raw, unstructured data directly from source systems, while a data lake stores only processed data. Option B, a data warehouse provides the breadth of raw data for exploratory analysis, while a data lake provides depth of structured, cleansed features. Option C, raw data is ingested into a data lake for initial storage and exploration, then refined and structured into a data warehouse to provide high-quality, historical features for ML models. Option D, both systems perform identical functions and are interchangeable for ML feature storage. The correct answer is, raw data is ingested into a data lake for initial storage and exploration, then refined and structured into a data warehouse to provide high-quality, historical features for ML models. Here's the explanation. Data lakes are excellent for storing raw, diverse data, while data warehouses refine and structure this data into high-quality, historical features, making them ideal backends for feature stores and model training. Question 16. Which of the following best describes the primary problem that Lakehouse architecture aims to solve? Option A, the high cost and complexity of deploying traditional relational databases for OLTP workloads. Option B, the challenge of combining the flexibility and cost-effectiveness of data lakes with the data quality and governance of data warehouses for diverse analytics and ML workloads. Option C, the difficulty in managing real-time streaming data ingestion into traditional data warehouses. Option D, the lack of open-source tools for building ETL pipelines in cloud environments. The correct answer is the challenge of combining the flexibility and cost-effectiveness of data lakes with the data quality and governance of data warehouses for diverse analytics and ML workloads. Here's the explanation. The Lakehouse architecture emerged to bridge the gap between traditional data lakes, flexible, cost-effective for raw data but lacking quality/governance, and data warehouses, strong quality/governance but rigid and expensive for raw data, creating a unified platform for both analytics and ML. Question 17. Which component is considered the cornerstone of the Lakehouse architecture, enabling data warehouse-like capabilities directly on top of open, scalable data lake storage? Option A, proprietary columnar databases. Option B, SQL-only query engine. Option C, open table formats like Delta Lake, Apache Iceberg, or Apache Hudi. Option D, dedicated ETL tools for data transformation. The correct answer is open table formats like Delta Lake, Apache Iceberg, or Apache Hudi. Here's the explanation. Open table formats such as Delta Lake, Apache Iceberg, and Apache Hudi are fundamental to the Lakehouse, providing ACID transactions, schema enforcement, data versioning, and other critical features directly on top of data lake storage. Question 18. An ML Ops team needs to ensure reproducibility for model training, requiring access to historical versions of their feature datasets. Which Lakehouse feature directly addresses this requirement? Option A. Separation of storage and compute. Option B. Data cataloging. Option C. Data versioning/time travel. Option D. Unified governance and security. The correct answer is data versioning/time travel. Here's the explanation. Data versioning, also known as time travel, is a key capability of Lakehouse architectures, enabled by open table formats, that allows users to access previous states or versions of data, which is crucial for ML model reproducibility, auditing, and debugging. Question 19. What is the primary goal of ML experiments within an ML Ops framework? Option A. To achieve immediate model deployment without validation. Option B. To systematically test hypotheses, track results, and improve model performance and reliability. Option C. To solely manage the versioning of code and data for compliance. Option D. To automate the entire model retraining process without human intervention. The correct answer is, quote, to systematically test hypotheses, track results, and improve model performance and reliability. Here's the explanation. ML experiments are the cornerstone of iterative model development, embodying the scientific method to systematically test hypotheses and improve model performance, robustness, and reliability. They are managed, tracked, and reproducible activities. Question 20. Which set of components is most crucial for ensuring reproducibility in ML experiments? Option A. Hyperparameter optimization, model artifact management, and visualization. Option B. Code versions, environment dependencies, and data versions. Option C. Performance metrics, start/end times, and run status. Option D. Collaboration tools, resource management, and UI dashboards. The correct answer is code versions, environment dependencies, and data versions. Here's the explanation. Reproducibility, the ability to recreate the exact conditions and results of a past experiment, is achieved by tracking code versions, e.g., Git commits, environment dependencies, e.g., Docker images, and data versions. Question 21. A data scientist is running an ML experiment to train a classification model. Which of the following would typically be logged as an LS artifact associated with the experiment run? Option A. The chosen learning rate, e.g., 0.01. Option B. The F1 score achieved on the validation set. Option C. The trained model file, e.g., a serialized TensorFlow model. Option D. The batch size used during training. The correct answer is the trained model file, e.g., a serialized TensorFlow model. Here's the explanation. Artifacts are files generated by the experiment, such as trained model files, plots, e.g., confusion matrices, or pre-processed data samples. Learning rate and batch size are parameters, while F1 score is a metric. Question 22. Which of the following best describes the primary goal of experiment tracking in ML Ops? Option A. To automatically retrain models when performance degrades in production. Option B. To systematically record and organize information about ML model training runs for reproducibility and comparison. Option C. To encrypt sensitive data and ensure data privacy during model training. Option D. To deploy models to various cloud environments with zero downtime. The correct answer is to systematically record and organize information about ML model training runs for reproducibility and comparison. Here's the explanation. The overview states that experiment tracking involves systematically recording and organizing all relevant information about machine learning model training runs, and provides a centralized, auditable record of each experiment, capturing crucial metadata such as input parameters, performance metrics, ensuring reproducibility, accelerates iteration cycles, facilitates model governance. Question 23. A data science team is using an experiment tracking system to compare hundreds of model training runs. They want to visualize how different learning rates affected the validation accuracy over epochs. Which key feature of an experiment tracking system enables this capability? Option A. Artifact management. Option B. Environment tracking. Option C. Visualization and comparison tools. Option D. Code versioning integration. The correct answer is visualization and comparison tools. Here's the explanation. The key features/components section lists visualization and comparison tools as a user interface or dashboard that allows for easy comparison of multiple experiment runs, visualization of metric trends over time, filtering, sorting, and analysis of results. Question 24. Which component of an experiment tracking system is responsible for storing large binary files, such as trained model files, pre-processed datasets, and evaluation plots? Option A, the metadata database. Option B, the tracking server. Option C, the artifact store. Option D, the SDK. The correct answer is the artifact store. Here's the explanation. The How It Works section explains that an object storage service, e.g. AWS S3, Azure Blob Storage, Google Cloud Storage, is used to store larger binary artifacts like trained models, datasets, or plots. And in the Key Features Components section, artifact management is described as storing and versioning all output artifacts generated by an experiment. These are typically stored in a dedicated artifact store. Question 25. What is the fundamental difference between a parameter and a hyperparameter in a machine learning model? Option A. Parameters are set manually before training, while hyperparameters are learned from the data during training. Option B. Parameters are internal variables learned from the training data, while hyperparameters are external configuration values set before training to control the learning process. Option C. Parameters define the model's architecture, while hyperparameters represent the model's predictive output. Option D. Parameters are only relevant during inference, while hyperparameters are only relevant during training. The correct answer is parameters are internal variables learned from the training data, while hyperparameters are external configuration values set before training to control the learning process. Here's the explanation. Parameters are internal variables of a machine learning model that are learned from the training data, representing the knowledge acquired. Hyperparameters, conversely, are external configuration values that are set times before the training process begins and control the learning process itself or the model's architecture. Question 26. Which of the following is an example of a hyperparameter? Option A, the weights in a neural network. Option B, the coefficients in a linear regression model. Option C, the learning rate for an optimizer. Option D, the centroids in K-means clustering. The correct answer is the learning rate for an optimizer. Here's the explanation. The learning rate for an optimizer is a hyperparameter, as it is an external configuration value set before training that controls the learning process. Weights, coefficients, and centroids are all examples of parameters that are learned by the model from the data. Question 27. In an ML ops pipeline, why is it crucial to log the specific hyperparameters used for each model training run? Option A. Hyperparameters are needed by the deployed model to make real-time predictions. Option B. Logging hyperparameters helps in tracking model performance, ensuring reproducibility, facilitating auditing, and comparing different experiments. Option C. Hyperparameters are automatically optimized by the model during the training process, and logging confirms this. Option D. Logging hyperparameters reduces the computational resources required for model training. The correct answer is logging hyperparameters helps in tracking model performance, ensuring reproducibility, facilitating auditing, and comparing different experiments. Here's the explanation. In MLOps, logging hyperparameters alongside model metrics and code is critical for reproducibility, debugging, and auditing. It allows ML engineers to compare different experiments and understand which hyperparameter combinations lead to better performance, rather than influencing real-time predictions or reducing compute resources directly. Question 28. What is the primary goal of metrics tracking in MLOps? Option A. To solely focus on improving model accuracy during the training phase. Option B. To provide transparency, enable data-driven decision-making, ensure model quality, and facilitate continuous improvement throughout the ML lifecycle. Option C. To exclusively monitor infrastructure-related metrics like CPU/GPU utilization in production. Option D. To manage and version different datasets used for model training. The correct answer is, quote, to provide transparency, enable data-driven decision-making, ensure model quality, and facilitate continuous improvement throughout the ML lifecycle. Here's the explanation. The primary goal of metrics tracking in MLOps is comprehensive, covering transparency, data-driven decisions, quality assurance, and continuous improvement across the entire ML lifecycle, not just isolated phases or metric types. Question 29. Which combination of metrics best represents the comprehensive tracking needed in a mature ML ops strategy, extending beyond just model training? Option A. Accuracy, precision, recall, and F1 score. Option B. CPU/GPU utilization, memory consumption, and disk I/O. Option C. Accuracy, inference latency, data drift indicators, and conversion rates. Option D. Perplexity, R-squared, MAE, and RMSE. The correct answer is accuracy, inference latency, data drift indicators, and conversion rates. Here's the explanation. A mature MLOps strategy tracks a diverse set of metrics, including model performance, accuracy, operational metrics, inference latency, data quality metrics, data drift indicators, and business metrics, conversion rates, reflecting the full lifecycle from development to production and business impact. Question 30. In an MLOps pipeline, what is a crucial step immediately following the aggregation and storage of production metrics to ensure continuous model reliability? Option A. Initiating a new model training experiment with different hyperparameters. Option B. Triggering alerts when metrics deviate significantly from expected baselines or predefined limits. Option C. Archiving the raw data used for model training to a cold storage tier. Option D. Developing new features for the next iteration of the model. The correct answer is, quote, triggering alerts when metrics deviate significantly from expected baselines or predefined limits. Here's the explanation. After aggregating and storing production metrics, the next crucial step for continuous reliability is to use alerting mechanisms. These mechanisms monitor metrics against baselines or thresholds, triggering notifications when issues like performance degradation or data drift are detected, prompting investigation and intervention. Thanks for watching. Please subscribe to my channel.